And I'm asking you to do a project. I'm going to give you some examples now of how I want to see it, okay? And how I would use StatCrunch. Unless you don't have StatCrunch, then you're going to have to figure a way of using it, I don't know, with a calculator or with Excel or whatever. Good luck on that part. So let's go back up here. I got some announcements here, and then I'm telling you about this midterm. Okay, so here's some examples. Now, the top is that you're already familiar with it. It's just how to graph the data, right? So I'm not even going to consider it. But if you need help grouping it up as a histogram or do a quartile, whatever, that's it. That's in the now. Here's what I'm looking for now. The traditional hypothesis test for whatever, and a randomized hypothesis test for, and it tells you what reasons for. So first you find out where's your fit, what type of distribution, and these are the confidence intervals. They'll be built into the midterm. You'll want the confidence intervals along with the test statistics, along with the p-value. Now, it's not, sounds like a lot, but it's not too bad. So let's take a look at, this is testing about a mean, okay, on raw data. I don't know if this will work. Okay. So I'm going to show you, because this one we can actually put into the, if you go to this link, right, and you click here, this is about apple juice. It'll load it directly into StatCrunch, for example, as an example. So let me show you what I mean. I go like this. Okay, so there I have, these are juice ounces that are fill a can of juice. You can see that there's a variation from can to can by a certain amount, okay? So when you're buying this from a supplier, because you're selling juice, let's say whatever, you'd like to know that they're getting the amount of fluid that they say they're delivering. Do you understand? That's how simple that is. So with this thing here, what's going to happen is that I might ask, I think that they're saying that 65.05, let's say, is the average, okay? So I can set up a hypothesis testing saying, you know, after I look at the data, first I can graph it, right? You want to graph it and take a look to see what, you know, what it looks like. And then just, oh, I hate that. Okay. So you get some feel of what it looks like. You have to calculate the summary statistics. What are they? You know, they're not an average, the deviation. So let me show you how this looks then. We'll follow along with it. So this is the first example of it. And the title is Conducting Hypothesis Test Now for the Mean. What is the mean called in the population? Mu, right? So you're going to be testing, you're going to be putting bounds around God's truth mu. Now this is how easy it is to run the test once you got the data. That's going to be your what you think God's truth is. But you suspect they're lying. So the alternative has the different ways you can put it in. Less than, greater than, or not equal to. She's going to pick less than because we're worried about there being less juice in a can than not. So your null hypothesis is this much, and your alternative is the other. That's it. You run the test. Oh, that's great.
In this video, you will learn to conduct a one-sample T hypothesis test with summary data using StatCrunch.
All right, so let me go back.
This example comes from Statistic.
Let's see. Okay, now, I don't want that. Okay, now, notice that what this says, conducting a hypothesis test from raw data. You can also, you can use summary, but I don't want you to use summary. I want you to use raw data.
This data set comes from Statistics, informed decisions using data to compute the appropriate one-sample T hypothesis.
Okay, so
Select the apple juice column. This is already chosen by default. 4.05 for the hypothesis to less than to 10.05 ounce state.
come on.
Including the
Okay, so this is what I want to see, obviously. This is going to tell you that there's your average, That's calculated for you. There's your standard deviation. This is your test statistic, minus 4.49, and that's your p-value, okay? Now, besides this, then, I want you to show this graphically as a t-distribution. So I want you to show this. Okay, so basically a t-distribution, what you're using is kind of a widespread bell curve, right? But what I want you to show here is that, first of all, remember what the confidence interval was. The confidence interval, I mean the degree of certainty that we want, if you recall, I think it was 95%. Okay, so that means that if I'm doing, this is a one-tail test. See it to the left. So what I'm saying, since my confidence interval in all cases, I'm saying I'm asking for you to look at a 95% confidence interval. That implies that 1 minus 0.95 is equal to 0.05, which is what we call our alpha. Alpha is how much stuff goes under the tail. Okay? So what I'm saying is that in this case, because it's a one-tail, I'm not going to divide alpha by 2. So the whole area here is 0.05. Okay? Now that's your test statistic, right? That's really right here. If I put a number here, it's going to be what you can calculate it, but it's be 4.49. See it from right here. Okay, that's minus 4.49. Now, if you want, you can look at the curve or the student t test, and you can see that the area under the curve here, this area that we're talking about, 0.05, you can look in the guts of the table, and remember how we were finding z-scores? This is a t-score. Okay? Actually, it's my bad now. This is not 4.9. Let me get rid of that because that's confusing. Hold on. I'll get rid of this. Okay. Now, what goes under here is what's called your critical value, right? That's the t that we have to find out what that t value is, okay? So, and then we have this, so some over here, somewhere, we're going to hit, like this is 0, right? So I think you can see that a standard deviation is really small. I'm thinking that the test statistic is going to hit here by a minus 4.490. You see where it's hitting? Okay, now, the p-value is the area under the curve from wherever the test statistic hits. So if the test statistic hits here, the area under the curve is this area, the one in red. Not the whole green, but this part. Okay, so if the p-value is less than the alpha value, if the p-value, this guy here, that's not proportion, okay? This means p-value. This doesn't mean proportion. P is being used a lot. But this is a p-value. If the p-value is larger, right, than the area from the alpha, so if it's larger than the alpha, see, then what you're going to do is reject the null hypothesis, and you will say that the evidence, you fail to reject, or you reject the null hypothesis in favor of the evidence that appears to favor the alternative. What is the alternative? Anybody see what the alternative is from there? It's less than 6.4, which means that there's a good chance that this stuff is not delivering as promised. Okay? So all of this, including the histogram of the data itself, right? I want all that. And obviously this. But that's all. So that's the case of a single variable, apple juice. Now, whether you run a t-squared or not, or a normal, will be based on some of the information that you have out there. Like, if sigma, if this is calculated, right, we don't know God's truth of sample deviation. If you don't know the God's sample actual true definition, usually you'll use a t distribution, which is has a little more wider, a little more lenient than the bell curve. But it's the same idea. You could probably run it on a bell curve too. Okay, let's do the next one. Show you this one. So actually, I got all of these already on Canvas. See.
I think you need to,
Let's see. Okay, so let's see. Where did I go for apple juice? I don't need that anymore. Okay, now here I do. I need to go back though. Let's see if I can go back to this. No, that won't work. Okay, so let me go back to the. Okay, that was. All of this has to do with graphing. I'm assuming you have somewhat familiar with it. And this is. Notice how this says summary. Do you see that? That's if remember how we can calculate the mean and the average by summary data? I don't want you to do summary data, okay? Forget summary data. So right now I'm not going to have you do anything that says summary on it. I want you to work it from the raw data. Okay. Actually, I want this one. Okay, so now here it is, but a proportion now. A proportion. Okay, suppose you have a proportion. Okay, now somebody tell me the difference between asking a question about a mean and asking a question about a proportion. What's the difference? What is a proportion? What does the word proportion mean?
It's like a small amount of the whole, or a percentage of
A proportion is a fraction, like a percentage. 30% is 30 over 100. So if I'm not asking particularly about a mean, but I'm asking in the world population, what percentage of people are born as midgets? That's a percentage. That's a ratio. That is a proportion. This is the kind of question you're asking. Now, not about the mean, but of some particular proportion, which might make for an more interesting project, but whatever. It's all good for, as I see it. Okay, so now this is the same thing. All right, but now we have raw data, right? But we're talking about proportion. Well, look how they put it. Somebody flipped coins. Head, tail, head, tail, head, tail. How easy is that? So they did it. Now, your hypothesis would be, is this a fair coin? 50% chance of getting ahead, right? If it's a fair. Of course, these only gone up to how many times we ran it. 50. Now we're ready to set up the hypothesis. Got to go to proportion and one sample with data. We'll have a 2 sample later on. Okay, now watch. We have to tell it what a success is. There's no numbers. It's quantitative. So you have to type in the word heads exactly as it shows. It's case sensitive. There it is. It's already P is 50%, and guess what this is? The alternative is not 50%. So that's going to be a two-tail test. This one, it decides a two-tail test. So let me see.
The test statistic and the p-value.
Okay, so that ran it pretty quickly for us. So let's take a look at this. There's this test statistic. This is the p-value. Remember, you could take a look at the p-value, right, and compare it to the alpha. Again, if we're talking about 95%, right, then alpha is 0.05, correct? Anybody? And if it's a two-tailed test, then you take alpha divided by 2. So you got, what, 0.025? And then I look, in my mind, I'm just looking to see if this is bigger or smaller than 0.025. That's called the p-value test. The test statistic way of doing it is you set up your confidence interval within your sketch and see where the test statistic hits, either in the reject or the accept. So, part of the problem that I'd like you to do then is that you're going to, sketch out whatever type of distribution you think it is, right? And then you're going to have the two-tailed part of it, remember? It always states earlier that the confidence interval was 95%. So that means alpha, if that's 90%, then alpha is equal to, 0.05, yeah? That's 1 minus 0.95. And so alpha divided by 2 is going to be 0.0025, right? That's what's going to be going into there. Okay, so here's you got your 0.0025 and your 0.0025, yeah? If you go into the either t distribution or whatever, you're going to find out, you're going to go from the guts of the table out, and you're going to find out how much area is from here to here. That's going to give you a z-value of approximately 1.96, let's say, or 1.96 over here, for example. Okay? Now, you're going to have to calculate your test statistic, and there is an equation for you to do that, and I simply am asking you to find out where does this test equation hit. So it's 1.696, right? So it's going to hit something like about right here. Do you see the test statistic? Actually, this is negative, isn't it? So I'm going to be over here because it's positive, isn't it? Okay, so when we got here, so this is our test statistic, a t-test or whatever we did. Could be a z-test, right? So is this hitting on the accept or the reject? This area here, anything, when the test statistic hits from here to here, it's an accept. Otherwise, it's a reject. So, on the one hand, I can look at it in terms of p-value and compare it to my alpha. I would say it's substantially bigger than 0.0025. Okay, so if it's bigger, that means there's more area from here on back. So this area in blue is what represents the p-value. All right? The area in green would be what represents the 0.025 in terms of a t or z score. Okay? So the area under your test statistic to the right or to the left is in fact the p-value. The area from the confidence interval 0.196 to the right comes out of your z-score or your t-score that you have to look up. Now, if you're using a t-score, you have something called the degrees of freedom, which is simply your sample size -1 in that case. Now, with all of these, to get a specific confidence interval, if you wanted to actually do that, then you can see what I had before was this. Oh. Okay, right down below here, if you want to figure out your confidence interval, here it is, how we set up the same thing now. We had a proportion, right? Proportion with raw data. Yeah? Now this is just for the confidence interval itself. But it's easy enough because you have to calculate an error term, remember? So it's God's truth bound by your best predictor. Plus and minus an error term. So this is the same thing again. Yeah.
should be 0.5.
And all of these examples you can load into StatDisk and try it.
Going to investigate is, due to the 50 outcomes in
It looks like the same problem, huh?
this data set,
Well, okay. Oh, calculating confidence interval.
to compute the appropriate confidence interval,
That's
under
okay.
the stat menu, I'll choose proportion stats, one sample, with data.
Oh, here it is. The lower limit
I'll select the point clicks column.
of your confidence interval. Okay.
Under success, I'll
Here's
determine
the
outcomes.
95% that we're saying.
In this case,
In this case, I'm leaving everything 95, but you can do 99, whatever you want. It depends how tight you want to make, how low you want to make the first type of error. That is saying something's true when it's not.
form, I'll choose confidence interval. By default, StatCrunch has a
Oh,
value of 0
it's already here, isn't it?
to 11.
I'll go back up.
Use the 95% confidence interval for the population proportion.
All right, here, there's a button for the confidence interval.
99 will produce a 99% confidence interval.
And you can pick the type of test you want there.
I'll leave it at 0.95 and click compute.
Oh, there we have it.
Show a 95% confidence interval for the long run proportion of heads, where L limit is the lower limit and U limit is the upper limit of the confidence interval.
Okay. So,
By default, StatCrunch uses the standard world normal approximation for calculating a confidence interval.
that's good enough. I'm not going to split hairs.
Alternative of resting pool model. To do so, under Options, choose Edit. This takes us back to the original window where we set up our confidence interval. Under Method, I'll change it to a resting pool and click Compute.
That doesn't really matter. I don't care.
The results now show a new confidence interval.
Okay. Oh, let's see.
In this video, you will
Okay. So that's a confidence interval, but it's embedded in the other one. So now in chapter 9, we're talking about comparing two means, which is real important because you could have a before and after or something compared to something else. So before I do that, we have this thing as a difference between paired data. Now, what is paired data? Anybody know? This makes for a good midterm. I mean, difference between two paired data. That is, that same person is paired from a before and after, or paired with whatever couple they go with. So let's take a look at that. First, we didn't do the difference of two means. Okay, so let's do the difference of two means. And in this guy, we're talking about bedroom prices. If you click this, this will pre-fill up your StatCrunch. And then you go here. Okay, so this one is talking about housing. And now we're going to have, watch how they separate the two categories. Two markets, one at College, this one in Bryant, Texas, and this one College State, Texas. Okay.
And
15 and 15, here and here. Square foot. We want to see if there's substantial difference in square feet. So 2 Tampa T. Okay, watch how they do it. Two sample. Two sample being this one and this one.
In the corresponding where box, I'm going to enter location equals Bryan, Texas.
Now,
To homes
now you're telling it where to look.
of Bryan, Texas.
So here I'm putting location, you know, either this one's Bryan, Texas, and this guy will be location, church. That has to be exactly like it is. See, it's going to split it up between Bryan and this. It's saying that the mu of 1, the difference between the two mu's is 0, meaning there is no difference in square footage by location. The alternative is that it is. So you say the alternative is that they're not equal to 0, meaning it's a two-tailed test. Confidence interval, you should check it there. Okay. I don't know if I can. You can look at the p-value, 0.7571. And this is the test statistic, okay? But remember what our alpha is. It's 0.0025. Do you remember? So which is bigger, the alpha or the p-value? And if you figure that out, are you accepting or are you rejecting the null hypothesis? We're accepting, right? Because this is a lot bigger than the alpha, meaning that in the test statistic, wherever it hits, the test statistic is, if it's a kind of a t-distribution, which is sort of look bell-like, so we're going to have our critical values that you have to calculate here. I'm not sure what they're going to be, but it's like 1.96. I think this is more for the bell curve, but that's okay. Under here, under each thing, we have 0.0025. 0.0025, you see? That area here, that 0.025 is equal to alpha. Okay, now, if you calculate the test statistic, and you're going to have to look up the equation for that test statistic, it should come out to that number. And you were to put that, that's 0.3. Remember, this is 0. So I know that the test statistic is hitting somewhere in here, the test statistic. Okay, is hitting somewhere in there. It's at point, so if this is 0.0, right? So this is 1, so it's something like here. And that is where we're hitting at 0.312, yes? Now the area from that test statistic back is your p-value. Do you see that the test statistic's hitting here? That is in the accept range. And you can see that this green is going to be bigger than the alpha. So they agree. In both cases, you are accepting. There's sufficient evidence to suspect that there's no difference. There's evidence to support the null. You're not rejecting it. You're accepting that there's no difference. There's no significant difference in square footage from one neighborhood to the other. Is it okay? That's 2. I like these because, of course, we're comparing 2 sections. It showed you how to peel off the data, too. Okay? And, oops. Okay. So now, if you look at it, you know, I told you to ignore the summary. You can if you want to, but I want to see the data. So this is a difference, right, between 2 means with raw data. And guess this is between means with paired data. So that means each person is before and after, for example. So this is conducting hypothesis testing. The difference means with paired data. The one was not paired, the one I just showed you. So let's see what this is. This is with a data pile that has to do with weight loss. Why is it paired? we have before and after for each individual person.
is called weight loss program. The data set is for a fictitious weight loss program.
What a great way to test.
Each of the 15 rows represents
How about if you have a new way of teaching?
weight before column,
Before and after grades.
in count, or under
Or class before.
and weight after
But this is actually paired to the person itself.
count after undergoing the weight loss program.
That's why we call it paired.
So, this video, the statistical question I'm going to test is there a significant decrease in the typical weight of a program participant? This can be tested by conducting a paired t-hypothesis test, or the difference between the mean weight after the program and the mean weight before the program. To compute the appropriate paired t-hypothesis test, under the stat menu, I'll choose t-stats.
Right? Paired. Okay, select in column 1.
I'll select the weight after column. And for sample 2, I'll select the weight before column.
You can obviously have to do histograms and drawings of. You can also do it of the difference, a histogram of the difference.
Hypothesis test is already selected by default. I'll keep the null value at 0 directly compared to mean difference.
That means there's been no change in weight loss. This is
Mean weight decrease after
alternative is that there has been a change. Now look, alpha, the confidence interval. Go ahead and click that. That's at 95%. That'll calculate it right there.
weight after the program is less than the mean weight before the program. I'll go ahead and click compute.
Okay.
The output
Now, this then, now we can look at our sample of our differences of about 6.33. That's not just the one, but of the difference of the two. Right, and the standard error, and there's our t-statistic. And look at that p-value. That's quite small. Much smaller than 0.025. Do you see that that's hitting in the reject area? So what are we rejecting? We're rejecting, or there's not sufficient evidence to support the null in favor that there was some weight difference, right? Now, notice what we did for our weight difference. How did we change it? We did it to less than 0. Because we want to know, right, either there was no gain or there was a loss in weight. So the data does not support the null, and the evidence seems to support the alternative, which means there's been a statistical, at the 95% thing, there is a statistical difference in rate over that period of time. Okay? Can you see that's much better than flipping a coin and just guessing? This thing is driven by the data to put a boundary around God's truth, which is pretty powerful.
The table shows various statistics from the test, including the test statistic and the p-value.
Okay, so this is proportions. You can start to see the same thing over and over, right? We have the raw data. We have of just one mean. We have raw data of two means. Yeah? Then we have proportion of one data, raw data. Yes? And then we have the difference of proportion. You see the same thing again? Now the difference with the tutorial, that's summary. We won't do that. This is the same thing now, but now we're going to be talking about top U.S. problems. This is according to what the presidents of the United States think. Now look at the quality of the kind of data that we have here. So it makes for an interesting thing. So now what they have is they have the presidents. Okay.
In this video,
Now.
we'll learn to conduct hypothesis tests for the difference between two proportions using stack count. The data set I'll be using is called Top U.S. Problems. This data set comes from a Gallup survey taken in July and August.
This is the party affiliation, and this is what they think is the number one problem in the country.
To name the biggest problem in the United States.
Dysfunctional government, economy, other, unemployment, immigration.
The response column contains the top column identified by the respondent. Only the top 4 responses are tabulated
binomial success, or you can use the bell curve. If now they're typing in the word immigration. It has to be exactly the same wording. This is like programming. You're telling it what to look, what data to call out. The first type is party equals Republican. Obviously, here is going to be party equals Democrat. I want you to click this too. Confidence interval. See, we want any kind of difference, either more or less. Okay. Now, our null hypothesis is that the two proportions there is no difference, whereas the alternative is that they're not. There's, when I say no difference, I mean the proportion minus 1 of the proportion number 2 is 0 difference, whereas the alternative is that there's something other than 0 difference. Whether that's statistically significant is bared out here. So if you take a look at this z-stat, that's my test statistic, right? You can see that's pretty far over to the right, isn't it? And this is a number that's 0.0001. That's pretty small, though. So even given that, remember, this is a two-tailed test, right? So I'm going to be comparing this with 0.0025. Oh, this is quite a bit bigger. I mean, the alpha is bigger, isn't it? So it looks to be like perhaps, even though this is really big, oh, this makes it look like it's going to be in the reject. How would it look? You know, whatever you're using, whatever distribution. The t-stat, this right here is the alpha, right? The alpha is 0.025 because we're basing it off of a confidence interval that's 95%. Now, if it's a two-tail, we had to divide that 5 into 0.0025. Okay, but our test statistic is hitting, like, we know this is something like 1.96. That is hitting way over to the right. That's in a reject area. What would the p-value look like? Well, the p-value is wherever that test statistic hits, remember? And that test statistic is way down there of 6.23, right? So this area right here, this teeny area, is the alpha. And I'm asking, does the p-value, I'm asking, is it greater than alpha? If it is, if this area from here, okay, so this area, you see here, the p-value is here. Is it greater? It's not, is it? The area from alpha is much bigger. Anyway, it's in the reject. So there really isn't any statistical difference in people analyzing the importance of immigration as far as Democrats, Republicans. You getting an idea what I'm looking for there in the midterm? Okay. Now, let's see.
Observe sample proportion of immigration responses between Republicans and Democrats, test statistic, and the p-value.
You can see it pretty soon. You can.
In this video, you will learn to conduct hypothesis tests for the difference between the two proportions with summary data.
How do I get back?
From a Gallup survey taken in July and August 2014, which asked 945 Republicans and 854 Democrats to name the biggest problem for the United States.
Well, that's okay.
Only the top 4 responses are
Let's see. I can't.
The number of Republicans classifying each as the top problem is
Okay. Let's see here. All right. So I'm back over to here. We're almost. This part here is chapter 9. Chapter 9. So this is a difference in two proportions, but we're not doing summary. Okay, summary is when it's already summarized for you. Do you remember the relative histogram? They already tell us how many frequencies fell in each cell, but we didn't have the actual raw data. So comparing two means, that's a lot like this. Comparing mean, but this is with two means. Okay, so this is not paired, and it's not proportions. Here we go. So on this one, we're going to use yellow-white exam. It says randomization test for two means. Well, let's see. Where is this thing anyway? Isn't there a movie here? Oh well. Okay, so we got the scores here, and then have yellow or white. So randomization test for two means option. After selecting the option, let's see. Okay, so exam will be equal to yellow, and where expression white, hit compute. So for sample 1, they picked the score, that's this column, and then they picked exam equals yellow. You have to define it. The exam equals what? Well, we call that yellow. And here we have the exam, because we're splitting it up in two data. You understand what I'm saying? It's one column, but we're going to split it up in two data sets. We're telling it how to split it up. We're going to call sample 2 the whites out of the column of exam. And we're going to call this one, yellow out of the column of exam, right? And then, since they're generating a random generator here, they're going to generate some data. Okay? Here's how many, 5,000. This is actually using this thing to generate a distribution. And here's the difference in means, see? Okay, here it is. It's called randomization. With the randomization approach, the goal is to understand the types of differences between the means of one might see if color has no impact. All right, and then to see if color does have an impact. To better understand the basic premise, begin clicking one time. So it's like running the experiment one time. It's generating a set of data for you. It's generating a randomized set of data with some kind of, we don't know the distribution yet, okay? So they're simulated, called a simulation. And the scenario where exam color has no impact on the outcome. Okay, the new window shows the difference between the mean score for the shuffle data. After the randomized reassignment is complete, this difference is dropped into the graph. Okay, so now they have the shuffling colors, and here's what they came up with. 75.5 of them were white and 79 tried. That's run one time, see it? This is one process. And so now we look at that, and we go to the next. And then we're going to try to run more simulations. So here we have the run times, time 1, times 5, times 6. And if you look at it, they've got 1, 2, 3, 4, 5, 6. Well, let's say 5 times. And this is the difference in means of the two. And there it is, after running it many, many times, we start to see, right, that in fact it's starting to look bell curve-like. Here's the ones that the difference landing within the range. Okay. So this is an interesting thing, because if you can generate the kind of data you're looking for, then you can use that as an experimentation in itself, because you're generating numbers which you believe to be of a certain distribution. So if you use a large number of randomizations, each time you made a set of data is one randomization, right? It is possible to consider the instructor's idea of yellow exams will lead to higher typical scores. And the random approach applied above shows the type of value you would expect to see for the difference of means if the color has no impact. So I guess the color of paper is supposed to have an impact on your grade. I'm not sure. The proportion, I mean, okay. These are above 6.3. You can play with that. And let's go back. And the last one is, well, this one's a summary. Oh, here. Comparing randomization. Same thing, but now with two proportions. But we're generating the data. It's generating it for us. It's a simulation. And if we have the right distribution and the simulation's producing data as though it were from that kind of distribution, then we can start answering questions about something that we're generating the data of that we believe is similar to the way it's being generated. Okay, so now we did the same thing, party and response. And then, and here we have the relative frequency. So you make a histogram out of that, see? And then here's the response. The economy here was 0.12, economy was 0.17. You want to see if there's a statistical difference? Then we run that test. You assign that party equals Republican, and this one response party equals Democrat. The success you have to write in as the economy. That's when they choose the economy as the more important thing, right? And then here's the range, difference in the proportions. And I don't know if you can see fundamentally the difference is that this is generating data on the fly and seeing how well your simulation is stacking up. So that's the difference. This one here, notice this is a shuffled. This one is the response. So this is randomizing out even the response. And now we're going to look at the difference of the proportions. That'll take some, I think. We'll do some more of that next time we meet. And again, now you're going to run the simulation 1, 5, or 1,000 times. And there it is. Any questions? This will take some, working on it a while because this is a little different. We're randomizing it. Yeah.
When we get our data, do you want us to print out the graphs and stuff from StatCrunch, or
Yeah.
just draw it all out?
You can.
Just print it?
Yeah. So I want you to show your confidence interval. I want to show your two ways to test it, right? Is the p-value test. And the other one is graphing where your t-statistic, where the test statistic is hitting. Right? Those are two ways of being able to accept or reject. Mm-hmm.
Are there trustworthy places to get good data?
I wouldn't get it from the White House if they have data there. There is a site that says White House data, so. But that's a personal opinion.
Like science data?
Science is good. I mean, data is everywhere. Everywhere. But if it were me, in order to make my life easier, I would probably peruse some other statistic books or produce other examples on the internet and track one of those and follow the data. Or if push comes to shove, your librarian is supposed to set you up with, you ask the kind of data you're looking for. They're supposed to help you find where it is. And then you have to come up with a reasonable hypothesis thing to test. A lot of it, if you want to use it in your own life, like you were doing something that you, in work, right? Yeah, so that would be even more ideal if you put something that maybe they would be of interest to know at your work, whether or not a certain hypothesis is supported or not. You can see that if you're going to do your master's degree or PhD and you're working on a thesis, a component of every PhD paper that has to do with proposing something new, this is to see if the data supports your philosophy. So part of it's quantitatively put into the thesis, right? Because you want evidence supporting, either supporting or not supporting, because by not supporting you also help understand a lot. It wasn't the case, but it was still a valid study. Any questions? Is it too easy? I think once you catch up, you'll see it's not that bad. It's just a matter of getting caught up, and then. So, you know, if you get this down good, I could just give you the results. You know, say in a final, and say, do you reject or do you accept? Here's results of some data. What does it show? How do you read it? And questions like that maybe you don't have to do a lot of calculation, but you have to do a lot of analysis. I don't have anything more unless you have a question more about something. Life in general, it's okay. Okay, I think that's good. It's a little early, but if you have any questions, you're welcome to stay.